First of all, I am very glad to be here. Well, thank you very much for inviting me here. So let me see. I started this one. So that title is Carbon Nanotube and Electron Microscopy. So I'm going to talk about two sort of main subjects. So what I'm going to do is the carbon nanotube emit audible sounds. So the first my subject, what the carbon nanotube, what is it for? How did you find it? Then the lastly, the modern electron microscopy of complex oxide. Nothing to do with the carbon nanotube, but I have been doing other things, so I like to talk about also. All right. So first one is the the carbon nanotube emit audible sound. I'm going to do some demonstration. Okay. So. Here is carbon nanotube, the black suit. Can you see it? Yeah. All right. So here is an ordinary flashlight, and the switch on. Okay. I shine the light.
You can hear the vibration. See that?
See?
It's very close to the microphone, so everybody hears.
Okay.
Can hear the
Microphone here.
No. Let me see. Yeah. Yes, hear it?
Can you hear it?
Wow.
Okay. So by shining the light, carbon nanotube emit audible sound. So why? What is the physics behind it? So this is very interesting. So I discovered it accidentally 2 years ago. Still, I'm working on this subject. So I'd like to introduce a little bit about this stuff now. Let's see. So, okay. So that's what I demonstrated here. The flashlight there, and the carbon nanotube, and the scale is about this side. Now, the carbon nanotube, and then the shine the light. This is the visible light, right? Okay, and then what happened here is we can hear the sound, audible sound. Okay, so carbon nanomaterial. So that's the what I did show you here. But phenomena, unfortunately, to me, discovered by the Graham Bell. The long time ago, 1881. So Graham Bell, he was the inventor of a telephone in Bell Lab, U.S. Okay, so he reported this phenomena already 150 years ago. So I was a little bit disappointed. Okay, but he don't use this LED light. He used the sunlight, and somehow shines some textile or suit. Then he observed this the audible sound. All right, but this is now happening to our nano material, nano-sized objects. Okay, so. Then when Graham Bell reported this one, his explanation was a little bit different. So actually he was wrong. And soon after, another physicist in UK, Tyndall, he gave the correct explanation. Okay, before that, this is my experimental setup. Yeah, very simple. Here is LED light. LED is white LED. Okay, so then he specifies me here. Right. So LED is actually this LED light. I have three the intensity. Okay, strong one is doesn't make sense. Okay, that makes the sound. And the second one, the third one, darker one give us the sound, audible sound. So that's explanation here, all right? These are pulse, okay? And the pulse frequency is this one is about 0.5 kHz, that audible sound, okay, frequency. So, but if you, I said, if you have the strongest one, it's just a straight, no the pulse oscillation. So in that case, we don't hear the sound. Now, so you get right. So next explanation is this. I said that we use this LED. LED has the rather wide the range of energies of light. So this is the close to near infrared light, right? So ordinarily the LED lamp only a few the small bands of light energies. So I think this the white LED is needed. So here's a specimen that shines light, and I pick up the sound by microphone and record it on PC. So that's very simple. And this is what I got the ordinary sound spectrum. And then here is the 500 hertz, that's this frequency here, right? So this is the fundamental, the sound frequency. And all these high order, the wavelengths, right? So that's what you listen to this sound. And then the explanation is like that. We have the carbon nanotube and then shine the light. This is the room temperature. Then shine the light. Then the surrounding the air molecule, that is the carbon nanotube, is going to be heated, so warmed up. Then the surrounding air molecule is also heated. So whenever we have the light on, the carbon nanotube is heated, and simultaneously surrounding molecules are heated, means expand because of heat, right? So then if it go off, then going back to the room temperature, and this is the pulse. Okay, so that if you repeat this on off, heating cooling, that makes the pressure difference, because when the air pressure goes up, heated, the pressure go up, the down. That's the sound. Okay, pressure difference. So that's what you heard from this the carbon nanotube. So this was the explanation given by the Tyndall phenomenon, the Tyndall motion, and then this Tyndall British physicist gave a right answer. This is why we can hear the sound. All right. So then the application of this. By listening, you can measure the weight, very small amount of weight, by hearing the sound. This is simple. The application, minimum detectable weight. How small amount of nanomaterial can be detected by hearing the sound. So I show you one of these. Okay. So this is my filtering paper, and I dropped the suspension of nanomaterial onto this paper. Very tiny amount, okay? This one, 7 microgram. It's white almost, and that increased the amount of suspension of, in this case, the carbon nanotube suspension, okay? So this is 80 microgram. Then I listened to the sound from these papers. So this is spectrum. 0.77 is this. And as you increase the amount of the material, carbon nanotube, you can hear more the sound. So this is sort of related to the weight of our nanomaterial. So in that way, we can measure the weight. All right. So now the another one is the you can plot like that. This is weight, and this is the strength of sound. So as you increase the weight, then sound get bigger and bigger. And some stage it's saturate. If it's too dark, then it's saturated. So in this region, very small amount you can measure it. So next one is the minimum weight of CNT and 30 nanometer gold nanoparticle. This is not carbon, but gold. Anything you can utilize this technique. I corrected this the amount on these papers. Are there steps? Continue? Okay. All right. So then this is the the materials, but still we have the some signal from the supporting paper itself. So then this is 8 nanogram this time. Okay, very small amount, but still I can hear some sound. And then this one is much more. So in this way, the minimum amount of detectable sound is something like that, nanogram scale. So so now this one, the gold. Many the biologists now try to use the nano gold particle. So this is suspension of 30 nanometer diameter gold particle. And then I did same experiment. I put a small amount of drop of this suspension of gold onto this paper. So small, then the amount of the gold particle there. So I can simulate the 0, and then we begin to see this here sound, right? So 2.6 microgram. I already pick up some sounds, very weak sound. So in this way, I proposed by hearing the sound from nanomaterial, you can measure the weight. You can guess what is the weight of your material. So this is the application. Then go next. Next application is the particle size measurement. Okay, if you change the size of your nanoparticle, also you can get some kind of information. This is diamond. Okay, this is the carbon material. So I prepared the different particle size of diamond powder. And then I had the 50 milligram gold powder. And then the size of those particles are changed. Okay, so let me see. Up here, the 0.2 micron diameter diamond powder. And then as you go down, this is the biggest one, about 25 micron, the diameter powder. So so weight is fixed, 50 milligram, okay? But the size is different. So in this way, if you have the bigger size, the sound is not strong. But as you decrease in diamond size, you can hear more sound, okay? So I said, if you measure like this, you can guess the particle size by hearing the audible sound. So I said, this kind of crazy experiment, no one reported yet, right? So, okay, so much about the application of this audible sound, right? Because this phenomena, the physical phenomena related to the surface, the area. specific surface area of your nanoparticle. Okay, as you decrease the particle size, the specific surface is going to be increased. Okay, so that's because if you have large the surface, then the surface hit by the air molecule and warmed up, heated up. So if you have the more surface area, then you can produce more sort of the heat. Okay, so all these related to surface area. If you have the bulk surface and do the same thing, nothing happens. So you must have the very small particles. All right, so that's all about this. Next one, what are carbon nanotubes? Let me see. Yes, I just explained quickly. So this is the carbon nanotube, just prepared by. This one is the vapor phase, the depositions. Yes, we call the DIPS method, right? So you can produce the carbon nanotube in that way. And then discovery carbon nanotube, 1991. And that's why I got a big King Faisal Prize yesterday because of this discovery. So yeah, thank you very much. Right, so yeah, this is the first report on Nature magazine, 1991. And then yes, when I reported this the experiment, some people wait a minute, I did this before you, and Russia, the Americans, some other the scientists, let's hang. Then no, you are not first guy to find the carbon nanotube. However, this is an important point. Okay. They reported something like carbon nanotube-like material, elongated carbon, but they don't know. There's no evidence this structure is really have the graphitic structure. Maybe amorphous carbon or other type of carbon. So what I did is I showed the electron diffraction pattern. That one, okay? If you see the diffraction pattern, then immediately, or I can say this structure is a graphitic, the graphite type structure. It's not amorphous, okay? So before my report, no one showed this kind of evidence to say the carbon nanotube. So that's why I got the King Faisal Prize. Okay, other guy before me, they didn't show this kind of scientific evidence. So we scientists are very important to show the clear the evidence for your discovery. Otherwise, some people don't believe your discovery. So please, you should demonstrate scientifically. All right, so much about this graphic structure. So only this black and white the TM pictures. I cannot tell this structure is graphite or not. But this is a necessity, right? All right, then we can say more detailed chiralities or armature or this kind of structure of nanochip. So these are also important, right? So this is about discovery, and then some of the physicists ask me, why don't you make the single wall carbon nanotube? First one is the second or multi-wall tube. So in order to characterize theoretically of these nanostructures, theoreticians try to start the calculation. Okay? But the thicker one, the double wall, those thicker tube, it's too big for the computer. Okay, so small size and the single is needed for the theoretician. Then I spent 3 years after the multiple, so the first paper, and because there's no recipe how to prepare the single carbon nanotube, so there's no information, but fortunately, accidentally happened to me. I found how to prepare the single carbon nanotube, but it took me 2-3 years. So I did this is 1993, so 2 years later, and so this is definitely again. I emphasize this electron diffraction pattern is important. This may be a black and white something elongated structure, but in order to say to be a graphitic structure, you need this one. But this is not easy to take a diffraction pattern from 1 nanometer object and ordinary electron microscopy. Fortunately, I have been trained as an electron microscopist for last 30 years before discovery carbon nanotube. So I can handle the electron microscope. So that helped me to find this one. Okay. So other experimentalists, if you are experimentalist, you have to have your own the best technique, because in that way you can differentiate from other guys. Okay, because if you use the same equipment, same approach, there is no difference. But if you have very good the world #1 sort of technique, they don't have it. So you can have you have a possibility to find a new phenomena, new material, new structures. Okay, so now this is about yes. Then once you have find this one, then you can study the detail of this material. So this is one of them. A few days later, we demonstrate this one. Then the one picture now, you don't need the diffraction pattern because high resolution electron micrograph can tell us what is atomic structures. Okay, so it depends on what your material. So in the case of carbon nanotube, high resolution microscopy did work. Right, so we can have this atomic model. Now, next one, what is it for? Application, right? Basic science, two-way. Maybe carbon nanotube can contribute to the basic science. Okay, so you are in the science department, the focus of science. But not engineering. They have a slightly different approach. Anyway, so basic science and application of carbon nanotube. I'd like to show you briefly. I am basically the scientist, not engineer. But we are doing the material science. So there's no clear boundary between these areas. So we go back and forth. Okay. So basic science contribution. Right. I said the basic science, physics, chemistry, nanoscience. So calculate the band structures or what's the mechanical property of carbon nanotubes are. So that kind of information you can predict from the theoretical the constellation. So that belongs to the basic science. Then industrial application, nanotechnologies. So in this category, I can show you the display devices, energy, battery, the fuel cell, the lithium batteries, electronic devices, structural material, fibers, film, medical diagnosis, testing medicine, the others. So a variety of applications are possible. But I can tell you, still no one could make a big money out of these applications. But maybe near future, someone could do it. All right, so I can go through this. Yes, this is the typical sort of science of material science. Okay, you can see this my title. So this atomic resolution electron microscopy of graphitic structure. So these are double wall carbon nanotube. Inside, we have a fluorine molecule. Scale is this is the distance between these lines at 3.4 angstrom, 0.34 nanometer graphitic structure. Okay, multiple. And interestingly, this the movie repeat, and I can go. We can wait at the beginning. Look at soon. Okay, so this is the beginning. Almost the same size, fluorine. The size is almost fluorine, C60. And some stage, I can see the dark dots. There's apparently the metallic atoms sitting on the surface. Then they started to grow. This guy don't have it, so stay in the same side. This one larger and larger. What you are seeing is the role of catalyst, atomic scale. Okay, so whenever you have a gold catalyst atoms on the surface, they can catch the carbon atoms and they put them into structure. That's why fluorine is growing. So this kind of nothing to do with application, but it's fun. Okay. So similarly, this one, the new one, in 2017, and people started to talk about the graphene. And then what we can do as electron microscopists, this is one of the interesting application. Graphene, one layer. Then these are in electron shower because we are looking at them in the electron microscope. So we hit the electron, okay? So that makes this kind of structural change. And at the beginning, this is connected. Then the bridge is formed, and the thinner and the thinner. And this is the beginning, okay? And this filament is a single carbon atoms chain. And at some stage, it's break. These are maybe the different, not carbon. You see? Single filament, and break. So yeah, this kind of now the people, if you have the carbon single filament, what is the carbon bonding? Carbon has four electrons, the outer electron. How these electrons are there in a single double chain or triple chain, one. Triple, one, triple, one, double. But so we can measure the atomic distance from this experiment. And so this kind of science of carbon, and yeah, this one is another one. These are different in the metal catalyst. So at the beginning, the junks are surface and connected. And this one is heated. Whole system is heated in electron microscope. So great change is taking place here. So in this way, how this the metal catalyst is important to control these graphitic structures. This is the beginning. Okay, in that way. So this kind of information we can get from the electron microscopy, and then why this happened, what is the energies, what is the electron, the stage, and so this kind of the research is proceeded. All right. So this is this is too much. Yeah. At the beginning, this one, okay. Here, probably this is single the metallic atom. We know this is tungsten. So Right. Yes, once you have the metal atoms on the surface, then they catch the carbon, double the carbon from the inside. Then they put them into network so that they can grow. Theoreticians try to calculate the energetic of this chemical reaction. This is all fun to do. Now this one is a carbon nanotube FED, field emission device. Okay, I have another demonstration here. Okay, this is the when we had this carbon nanotube, many industry people excited about this application. Okay, so this is I switched on. Oops. Yeah, switched on. This is again lamp. Okay, but this is a carbon nanotube lamp. Okay, and this is a vacuum tube, right? But inside the carbon nanotube, and then the carbon nanotube emits the electron, and he hits the fluorescence material here, so that like a fluorescent light. But this one is like that. So this is interesting application. Let me explain about a little bit more that. Yes, here in the tube, we can have the carbon nanotube, and then here is a fluorescent screen. So it shines. All right, because carbon nanotube is very needle. They have very sharp point. Okay, so this is important, right? Like that, the nanoscale, needle. And then it's for the high school boy explanation, okay? If you're lightning rod and you have thunder, and then it hits the here. So what happens? Lightning rod there, then yes. So up here we have cloud, and then they have a bunch of the plus ion, and then because all this electric field they come to tip of this here, so electron is sucked up from the ground, okay, and they go cloud. Exactly same thing happened to our lamp. Here, carbon nanotube, we applied the potential between carbon nanotube and, because it is very sharp needle. Then the electron is sucked out from the tip of carbon nanotube, and it goes through this, go to this screen, and then like the fluorescent bulb. So this is simple explanation of this, and let me see. Right. Let me see. Before that, so I said this is a huge bulb, but industrial people try to make it to the miniature, even a millimeter size of this bulb, and what they do is put them in the panel, so that they can have the flat panel display. Actually, Samsung, the Japanese electronics company, worked hard to make the display. However, this is too expensive, and then technologically it's defeated by much simpler the LED or some organic the material, emitting material, or OLED. Okay, so this is disappeared. Unfortunately, but the science is still very interesting, and some of the American professor tried to use this technique for not the display but the but the X-ray the production. I'm going to explain this one, right? Here we have carbon nanotube. and the hit the metal surface. So in that way, we can produce X-ray. So remember, this is the very tiny, small nanoscale things, and hits the metal and generate the X-ray. So this can be used for the X-ray generator or imaging. And this is commercially now available. If you go to the dentist, they took your X-ray pictures, small X-ray camera. Or in old days, if you go to the medical doctor, you have the big chest, the images. So I think this one is a very handy, small scale, the X-ray, the imaging. So this is commercialized. It's quite new, 2021, and even this is a very visible application. If you go to the airport, your luggage will be checked, and the big machine. Okay, we put our luggage to this machine, and then they try to detect what's dangerous things are in it. So this is done by the X-ray, the imaging. So now this professor replaced the conventional X-ray generator with a carbon nanotube like that. So this is actually a commercial one. And some airport, he said, already installed. So this is another application. Let me see. Then last one is, we have been doing a little bit about this application. This is medical diagnosis, biology, or medicine application. Because when you have the single carbon nanotube and it shines near infrared, then the carbon nanotube emits the fluorescence light. Okay, so this is the point. The carbon nanotube is very the special properties. This is one of them, fluorescence emissions. So this can be used medical diagnosis, drug test. So yeah, also single carbon nanotube already very good the emitter, fluorescence emitter. But if you modified the surface of carbon nanotube for epoxide or ether, so the emission increased more. So in this way, try to use, okay, pristine CNT is that much. And if you modify it, so you can get more emission. So that can be used for our body. So these mice, we inject the carbon nanotube in the bloodline. So then shine the near infrared light. Near infrared light can go to penetrate our body a little bit, maybe 10 centimeters. Okay, so in this way, then they shine the carbon nanotube in the bloodline. So it emits the fluorescent light. So in that way, you can see the inside of the mice or even our body. So this one is moving, no? It's heart or somewhere, kidney or then the moving. It didn't work, but oh yeah, yes, like that. So the carbon nanotube can be used for this diagnosis or the medical application. So still people working on this, but in this area there are many other material can do things. All right, so now how did you find the carbon nanotube? So this is the right. So high resolution electron microscopy. Already I introduced how the electron microscopy is important to do something, the new nano material. You can have other technique. In my case, I use the electron microscopes. Okay. So I can quickly go through the before the discovery of carbon nanotube, what Iijimas has been doing. Many people don't know what I have been doing, right? So because this is rather important to find carbon nanotube. That's why I tried to explain this, right? So yes, and this I stole this picture from Kittel of solid state physics book, and this is at that time many years ago the typical electron micrograph and the information you can get. These are dislocations in the bulk material. Then, so this is in 1971, okay? So carbon nanotube discovery is the 1991. So this one in 1971, 20 years ago. So I had this one. I said the first atomic resolution images recorded in 1971, okay? So at that time, the physicists or metallurgists talking about this kind of information. Then this one, completely different information, okay? So I started this one. When I finished my PhD, and then I moved to the Arizona, US, and then where we started the microscope group there. My boss is John Cowley, anyway. So then fortunately, I moved to Arizona in 1970. 1 year later, I could this image. So I think people will be surprised because it's so far talking about this. So entirely the different type of information are available from carbon, the electron microscopy. So I did a lot of application. This one is John Cowley. He's originally Australian, but the same time we moved to Arizona, and I joined the John Cowley's group. And this is at the beginning, and this group, his group is becoming larger, and in the States, and so it's kind of world center of electron microscopy. So I was there then right. Okay, so and then one of our application TI2 NV10 or 29. I can tell you later. Now, right now, this time, people talking about this material, okay? I did it 30 years ago, 40 years ago. I did a lot this experiment, but now lithium battery people talking about this material. So I can tell you the last part of my all right. So yes, I moved to Arizona. Then I started to do the high resolution. How can we see the individual atoms under the electron microscope? That was a big subject in 1970. Okay, so many people working on who is going to be the first guy to be able to see the individual atoms under the microscope. So I was involved in this competition, and then this is my effort. Okay, I prepared very thin graphene film. If you try to image atoms, single atoms, one atoms, how do you suspend in a microscope? You need some substrate. Okay, because this is single atom, so you need a very thin, transparent, noiseless the supporting film. The carbon at that time, the carbon deposited carbon film, amorphous film, it has the noise, so you cannot use the carbon, the amorphous film. So, but if you have a crystalline film, the noiseless, the supporting film you can have. So I prepared the thin graphite film. By the way, this technique, peeling off the graphite from bulk, that was what's the Nobel laureate of graphene. Yeah. They did this one, but I 30 years ago I did this one also. They prepared thin graphene film, but my purpose is different. Like that, see, and then I deposited the single atom, in this case tungsten, heavy atoms. So the same area. Then after deposition in situ deposition, so same area, because if I show this only these pictures, maybe people don't believe what they are. I'm saying this. Hey, look at this single, very small one. This might be the single atom. So I was the first guy to see the single atoms under the microscope. So, but ordinarily people don't accept this my experiment. So you have to show the a lot of evidence. Okay, if I show only this one, people don't believe. But before that, deposition. Okay, so nothing there. After deposition, something happened here. So if you become not a small one, might be single atoms. So I said this in 1970. I was the first guy to see the single atoms. There are a lot of arguments about this. So I was involved in this one. Important point, this is carbon, okay, graphene related to the carbon nanotube, okay? And this one, another one, in that time, this is done when I was at Cambridge. I stayed there for the short time. Anyway, 1980. I devoted this one. These days, this structure is the multiple carbon nanotube, okay? I devoted this one in 1980. But yes, I said this is multiple tube something. But my interest is not those entire structure. My interest is this here. Okay, all right. Here is something lines, because in order to see the individual atoms, it's rather difficult. But if you have single atom the sheet and the edge-on imaging, that's easier to see than to see the individual atoms, because this is single atom plane, the edge-on images. So this is carbon, and then you see this. So then I said this is single graphene sort of structured, and I said in the paper I said, tubular-shaped particle of graphitic carbon. Okay, this is multiple carbon nanotube. And this, I was reported this one 1980. Remember the discovery of carbon nanotube in 1991. So more than 10 years before the discovery, I already had this experience. So I know later on when I saw this elongated one, hey, look. This is very much similar to what I have seen before. This one, it's okay. Right now, also, this is another important point because I missed the Nobel Prize because I tell you, okay. This is I think here. I prefer this one. People say the onion structure, okay. And these are onion structures, right? Then in this paper, I show this one here. And I emphasize, look at the inside, this small circle, this one. This one is almost same as the 0.6, the nanometer sort of spherical, the structure, something. So then these papers, I didn't show this one, but very interestingly, I said somewhere, pentagonal rings. In order to explain this curved onion structure, it's not a hexagonal network. We need a pentagonal. I said this one here, okay? And even the appendix, I said, yeah, there must always be 12 pentagon. If you look at the soccer ball, you can count the 1, 2, 3, 4, altogether 12. Okay, that's fullerene carbon is 60. So but I wasn't smart enough. I cannot say this is fullerene structure. If I smart enough, I said hey, this is soccer ball structure, consisting of 60 carbon atoms. Then I might have the Nobel Prize instead of the highly clotted small. So But this is very interesting later on because can I have the time? Or? Okay, I can continue. All right. When the Sumio Kroto reported of carbon 60 and then 1985. So this is 87. Oh, this is 80. So okay. 5 years later, they reported the fluorine in Nature. But those papers, not many people believe because their evidence is not good enough because they only show the mass spectrum, big C60 peak, 70 peak, but they don't say the structure. Maybe some cluster of carbon 60 carbon atoms, maybe change, maybe something, but they predict 60 carbon atoms should have the suckable structure. So this is a speculation, okay? Speculation is not science, okay? That's why the researchers don't believe their papers, okay? Could be suckable, could be something else. So they started to see the evidence to support their discovery. And they came to me, came to Japan because somehow they find this paper. And then I said, this is structure. So, but not this one yet, but because this onion structure here in the center. So this is the only the evidence to support their postulation because ring structures. Then this was before they received the Nobel Prize. This is only evidence to support their proposal, C60 molecular structure. So in that way, I had a connection with Harry Kroto Sumio because I am very important guys to support their finding. Okay, so all right. Oh, this is crystal side. Okay, we are talking about the molecular C60. This is general sort of explanation. If you have the smaller structure, then physical, chemical, all the property can be different. So yeah, all right. And then yeah. So another example, this is not carbon, but this is gold. It didn't go. Sorry. This is actually the video, the pictures, the very small gold particle. I showed the suspension of gold, okay? The red colors, the plasmonic colors. But this one is not this. This is only structured. Also, I reported this experiment 86 before the carbon nanochip, and the small, because at that time we were interested in anything small structures, because this is one of the typical one. So if you look at them under the electron microscope, shape and inside the atomic structure is always changing, unstable structures. Yeah, structural instability. That's because already theoretically it predicts if you have a smaller the structure. So for instance, it's melting to the point is going to be decreased. So like that. So whenever you have the small the structure, it's different from the bulk structure. Yeah, that's right. If you look at this the bulk gold, nothing happens. But if you make it smaller, then you can have interesting property. Okay, yeah. This come back to the Harry Kroto. This actually border the north, the Israel, and then another country. So when we had the meeting, the Israel, we went to the border here. Okay, anyway. So the discovery of carbon nanotube, all right. So yeah, this is another explanation. The arc discharge method to prepare carbon nanotube. This is, if you go construction site, you see this the arc, the welding. So this white smoke is nano oxide, nanoparticle. So exactly same thing. I have the carbon dots and do the arc discharge. And then you have the smoke. Inside smoke, you can find C60. Not a single carbon nanotube yet. But in this smoke, we can produce C60 by this arc discharge method. But I looked at this electrode and the debris after the evaporation. Something developed on the surface. And then they scratched off the surface and put them in microscope. That's the discovery of carbon nanotube, okay? So at that time, people were talking about the C60. Right, so yes. Then I talked about this one, and the Kuroto, the Smori, I had a very close connection with them. Then yes, I said somewhere the discovery multiple carbon nanotube. Okay, yeah. Then because already I acquainted with this the Nobel laureate before, and then the 1990 there was a big conference in the material science in the U.S. and Boston, and maybe people talking about the superconductivity of C60. Then I met the Smori, the Kuroto, yes, and then they said you should work on the fullerene, because already we had some relationship, and then they worked on the carbon material. So they come back from Boston, the meeting, MR's meeting. Then I started the onion structure again. However, fortunately, I can see all this onion structure everywhere. But if you look at it closely, something else happening here. Elongated, tiny filaments are everywhere. So that's the discovery of carbon nanotube, very thin filament. Originally, as I said, I started to examine all these onion type structure, but rather than that, something else there. So that's why accidentally I came across the filament. Then yes, this is another my experience. When I was a master student, I have been working on this filament, and part of my doctoral thesis is about this. This is silver metal. Somehow silver, the metal filament growing. This is not a single crystal, but this is very unusual. If you grow any material, always you have sort of bulk block. It's not go like that, and it's a tropic, the growth. So I checked what happened the filament, and I found the defect, which is a twin defect along the filament axis. So that makes the anisotropic crystal growth. So I had this kind of experiment, and then I saw this peculiar the filament in the fullerene onions. I immediately come back to this image. Because I had this experience already when I was a student. So this memory immediately come back to me. Then this is very much similar to the silver filament. So I know how to know the structure using electron diffraction method. So I did immediate. Okay, all right. So I think this is another one. So I can go last one. Modern electron microscope, complex oxide. So nothing to do with the carbon, but this is atomic resolution, EDS STEM imaging. Okay, I go quickly. This is old one, the development of new microscope. Starts in 90s Arizona, and then these are sophisticated microscope these days. And now I want to show you some of the results taken by this modern microscope. What you can do, the X-ray the imaging, EDX, what we call. Yeah, this is right. I show you this, and then linear change. Then yeah, this is yeah. Come back to here, and this is niobium tungsten, niobium oxide. Okay, the because non-stoichiometric structures, oxygen is missing. Anyway, non-stoichiometry, and then already at that time there are a lot of the defects there. So then this is old work, but I analyzed what happened this earlier here. So I can propose this kind of defect in the structure, the oxide structures. Then, yes, this is current the interest published in 2021, and now people the titanium aluminum oxide from discovery of application in the first charging lithium-ion batteries. Okay, this paper came out from the Cambridge chemistry group 2 years ago, and this oxide might be used for the solid iron battery. So then here now, okay. So right. Yeah, there are many the report about this material for the lithium, but here the titanium is talking about this one. So I had this one Ti2NV10 or 29 for 50 years ago. So I started to check this material, and these people say the solid solution, the titanium niobium oxide, the ternary oxide, but they don't know exactly titanium and niobium how they are arranged. X-ray cannot distinguish. So then this is a good subject. Yes, we use this X-ray imaging, atomic X-ray imaging, so that we can now tell where it's the titanium, where is the niobium. So this is all the pictures, black and white. But the structure is we know, but we don't know how the two different atoms, metal atoms, are distributed. And then 50 years later, I also reported this one. So STEM, scanning transmission electron microscopy, and the X-ray imaging. So these are the same black and white the images, but still we don't differentiate the two types of metals. But now solid solution here, but now we can get these images. Same. So titanium here, niobium pink. So we can distinguish where they are. So this kind of information is needed. But I said the lithium battery people ignore this kind of the property structures. So they needed this kind of information. So I did a lot of this and quantify this imaging. And all right. So I think still I am interested in what I can do using electron microscope. All right. So modern electron microscope group. Right. So I finish my talk. Okay, thank you very much for your attention.
Thank you very much for
Well, thank you for
visiting
inviting
us
me.
and for this lectures. It's great. Okay.